In this video, we're going to introduce another concept that is part of our curve analysis series, and that concept is concavity, right? So it's another property that a function can have, and the goal, again, is to be able to understand this property using derivatives, right? Now, again, as with all of these, we're going to start with pictures. So I am going to draw two curves, and they're going to look like parabolas. I'm going to have one that opens up like this, and then another one that opens down like this, right? Now, you notice, so if you think about what we've previously done with the analysis of curves and talking about how derivatives affect certain properties of the graph, you can see, for instance, this one is decreasing and then increasing, and then this one is increasing and then decreasing. So both of these exhibit the two main properties that we've talked about, right? But to introduce this idea of concavity, what I'm going to do is on each of these, I am going to draw some tangent lines. So let's say, yes, I'm going to draw a few tangent lines. I'm not going to extend them too far, right? But here are some tangent lines. Like that one, right? And then let's draw some tangent lines over here as well, like there, and there, and there, there, and there. All right, good. So we got our tangent lines. Now let's just make some observations about these, right? And let's start with the ones in blue. You know what's interesting is it appears that no matter what portion of the graph I drew the tangent lines on, it seems like they were either we know that they touched the graph, but it looks like the tangent lines are actually supporting. It's almost like the tangent lines are holding up this graph. It's like pushing the graph up. Notice how all the blue lines they either touch the graph or they're below, right? So for instance, you can see these little gaps between the curve and the tangent line. So one interesting observation here is that when your graph has this kind of shape, right, all tangent lines lie on or below the graph, right? So all tangent lines lie on, meaning, so we know that they have a point in common, and that's the point we often use to find the equation of the tangent. But then otherwise, they're or below the graph. All right, so that's kind of an interesting, I guess, kind of geometric way of looking at this. But now let's consider the slopes of these lines in sequence, going from left to right. So for instance, this one is sloping down pretty steeply. So for instance, all of these on this portion would have a negative slope. That's why the graph is decreasing, right? But if you look at how the slopes actually compare, this slope is not quite as steep, right? Or not quite as negative as this slope. So just to kind of put it, to make it a little bit easier to see what I'm trying to highlight here, let's just put some numbers, right, that could represent the slopes of these blue lines. Let's do that, right? So for instance, this one, let's say this is like a -7 slope, right? Well, this one might be a -4 slope because it's not quite as steep as this one. And then this slope, maybe it's like negative 1.5, something like that. But then look what happens over here. It now changes to a positive slope. So maybe this would be like a 2.1 slope, and then maybe this would be a 5, a slope of 5. So look at those numbers. We can say that the slope of the tangent lines, right, is increasing because they're getting bigger. The numbers are literally getting bigger. Negative 7, negative 4, negative 1.5, 2.15. The slopes, as I go from left to right, are getting bigger. That's an interesting observation. So the slopes of the tangent line, right, are increasing. Wait, where have I heard that word? We've talked about this recently, increasing. So let's see if we can translate this now into derivatives, right? So the slopes of our tangent lines are getting bigger, they're increasing. So we know that the slope of the tangent line is found by the derivative, right? So in other words, take out the phrase. And in fact, let me change it this way. Let's make it singular. So the slope of the tangent line is increasing. Let's do that. So take out this phrase, slope of the tangent line, and insert the word derivative, because we know the derivative is the slope of the tangent line. So the derivative, right, is increasing. That's also interesting, right? All right, so let's kind of stop there in a second. So these are just some observations, right? But we're close to what we need. We're close to what we need in terms of defining this idea of concavity and then determining a way of how can we figure out when a graph looks like this versus like this, all right? But let's do something similar with the red tangent lines, right? Well, now that we kind of know what to look for, right? We just, we will have analogies of each of these bullets, right, on this side. So if we look at it, all the tangent lines now, they seem to be, it's almost like they're pushing down the curve. Notice they either touch the curve or they're above the curve. So all tangent lines lie on or above the graph, right? Now let's look at what these slopes would be doing from left to right. So this is a fairly steep positive slope, so maybe this one's a 6, and then this one maybe I don't know, 2.9, and then maybe this is just like a negative 0.9, and then this, now they're getting more and more, there's more and more negative, right? So on this side, maybe this is a negative 3, and then this, maybe this is a negative 7, right? So yeah, look at the numbers. 6, 2.9, negative 0.9, negative 3, negative 7. All these slopes are getting smaller. They're decreasing. You start out from a relatively large positive number, and then you get it's hard to say a large negative number, but yeah, let's say that we get a large number in magnitude, but it's negative, right? So let's again write the analogy of this one. So the slope of the tangent line is now decreasing. Well, yeah, again, slope of the tangent line. Just insert derivative there. So take out that phrase, slope of the tangent line, and what we can say is the derivative is now decreasing. Right? And it's the third bullet point that we're going to use to define concavity. Right? So whenever the derivative of a function is increasing, we say that the graph is concave upward. So it looks like this. It looks like a cup, right? So this type of, when your graph has this kind of shape, it's said to be concave upward. It's almost like a cup. So like if you were to pour water into a graph that has this kind of shape, then the water would settle. So it would hold the water. Right? So concave up like a cup. On this side, again, whenever your derivative is decreasing, right? So in other words, the derivative of this function that I originally drew, the one that we're now defining in terms of its concavity, that function, when its derivative is decreasing, we say that the function is concave downward, right? Or just concave down. And if you were to try to pour water on this, then it would just it would spill the water, right? It couldn't hold the water. Or another way to say it looks like a frown. So you could say it's concave down like a frown. So concave up like a cup, concave down like a frown. But again, we can define these two properties in terms of the derivative. All right. So let's go ahead and again write down that definition formally. Now, so if f is differentiable, right? So we have to make sure that the derivative exists before we talk about things like, increasing, decreasing, and as far as it relates to the derivative. So if f is differentiable on an open interval, then f is said to be concave up. So concave up on that interval if its derivative is increasing. So if f prime is increasing, right? And f is said to be concave down on the interval if f prime is decreasing. Right? So what we're defining here now is the property of concavity, and a function can either be concave up or concave down on an interval, and by definition it's when the derivative is either increasing or decreasing, right? And that's good, but let's do some more translations, right? Because we now know what it means for a function to be increasing. So let's say this. So if f prime is increasing, remember what it means for a function to be increasing is its derivative must be positive. So then what this means is that the derivative, assuming my function is a function of x, so my derivative of f prime would have to be positive, right? If f prime is increasing, then f prime must have a positive derivative. But what is the derivative of the first derivative? That's the second derivative. So that means f double prime would have to be positive, right? And that's the connection between, now we already have a connection between concavity and a derivative, but now we've related it to where the second derivative is positive, right? And then similarly, if f prime is decreasing, then that means the derivative of f prime must be negative. Oh, must be negative. Right? Well, again, the derivative of the first derivative is the second derivative. So your second derivative would have to be negative. Now, this assumes that the function is twice differentiable. So you can differentiate it once, you can differentiate it twice. So we can actually take the concepts that were developed earlier in terms of increasing or decreasing, right? And then relate it back to this idea of concavity, right? So here is a theorem now that tells us if I have my function f of x, what is a surefire way to determine when that function is concave up and when that function is concave down, right? So here's our theorem, right? So again, this is a definition, this is our theorem. So let f be twice differentiable. That means I can differentiate it twice and the second derivative still exists on an open interval. All right. So two simple conclusions. So if the second derivative is now positive, so if f prime of x is positive for all x in this open interval, then the original function f up here is going to be concave up. So then f of x is concave up on that interval. So concave up on that interval. All right. So that's the test for concavity, or upward concavity, I guess. And then B, so all I have to do is switch that inequality to a less than, and then switch the up to a down. So if f prime of x is less than 0 for all x in this open interval, then our original function is going to be concave down on that interval. So basically a really nice analogy, and maybe I should do that here before, because there's one other thing we need to define, but maybe I'll do the analogy right now. What the first derivative is to increase or decrease, the second derivative is to concavity, like concave up, concave down, right? So that's a good analogy to kind of think of. I use the first derivative of the function to indicate or to determine when that function is increasing or decreasing, and I used the second derivative of the function to determine where that function is concave up or concave down. All right? Now, there's one other thing we need to think of, and that is, could we have a function where a part of it is concave up and a part of it is concave down? Yes, we can. In fact, let me show you what that curve would look like. So something like this, or something like, oh, let me switch this. Do it this way, so down, then up, right? Yeah, so for instance, here's our cup. Here's our cup. And here's our frown. And here it's kind of flipped. Here is the frown. Here is the cup. So something has to happen here for it to change from concave upward to concave downward. So now, I can't say like, it's not like increasing or decreasing, because here it is decreasing and then it's increasing. But along that whole interval, right, this whole portion of the graph is concave up. Similarly over here, this portion of the graph is concave up. So concave up. And then this portion of the graph and this portion of the graph, right, is concave down. Right? Here and there. Concave down. So something has to happen. There's got to be a point here, right, where so again, and what I'm going to do in a second, I'll put what it means about the second derivative, right? So for this portion of the graph now, its second derivative would always be positive. Similarly over here, the second derivative along at each of these points on our graph would have to be positive. Here, for all of these points, the second derivative would have to be negative. And similarly, here, the second derivative would have to be negative. So something would have to cause the second derivative to change from a positive sign to a negative sign, or from a negative sign to a positive sign. And the points at which that occurs, so now let me kind of indicate it there, points at which the concavity of a function changes, these are called inflection points, right? So let me write that here. So points at which the concavity of a function changes, whether it changes from up to down or down to up, right? So wherever the concavity of a function changes is called an inflection point. Right? And so so this portion of our curve analysis, the questions will entail finding where the function looks like a cup, or where does the function look like a frown, and then where does it change from one to the other. Right? It sounds very similar to when we did increase and decrease, and then you had like the relative min and the relative max. And it's at those points where your function changes from increasing to decreasing. So to continue with that analogy, what relative min and relative max are to increase and decrease, inflection points are to concavity, right? So again, lots of analogies between these concepts. So let's take a look at a question where it should show you what you'd be asked to do regarding concavity, right? So here's an example. And again, if you think of our series of the curve analysis, we've done examples that involve polynomials, and then more general power functions that are not polynomials. Now let's do a completely different type. Let's say it's like the product of a polynomial and an exponential. So find the intervals over which, and here's our function, f of x equals, so let's say something like x times e to the negative x. So find the intervals over which this function is concave up or concave down, right? And then second, identify all values of x at which the function has an inflection point. So identify all values of x at which f of x has an inflection point. Right? Okay, so let's look, for instance, so look at what we have to do. Essentially, this picture gives us a template of what we need to do to answer this question. So in order to identify the intervals of upward concavity or downward concavity, we're going to have to solve inequalities again, but now these inequalities involve the second derivative. So we have to determine where the second derivative is positive, and that would correspond to intervals of upward concavity. And then where the second derivative is negative, that would correspond to intervals of downward concavity. And then where the second derivative changes from either positive to negative or negative to positive, that's where the function would have an inflection point. All right. So if we take a look at this function, so let's start with so just another note. It's always important to identify the domain of this function, and the domain of the polynomial x is all real numbers. The domain of the exponential function e to the negative x is all real numbers. So the domain of the product is all real numbers. So just make a note, the domain of f of x is negative infinity to positive infinity. All right. So what we have to do is differentiate this function twice. So that's the calculus part, right? And then we're going to have to find the zeros of the second derivative. And again, we're going to use a number line to help us figure out the solution to these what will be nonlinear inequalities, right? So let's start by finding our derivatives. So our first derivative requires the product rule. So the derivative of the first is 1 times the second plus the first times the derivative of the second, and the derivative of e to the negative x is e to the negative x, and then our chain rule says we have to multiply by that negative 1. So we end up with e to the negative x minus x e to the negative x. Now, to differentiate this, notice that e to the negative x is a common factor. So we can factor out the e to the negative x, and it will make the second derivative a little bit easier to find. So when I factor out an e to the negative x, I have my 1 here, and then I have my negative x here. All right? And if we wanted to, we could put the polynomial in front. We could put the 1 minus x as the first factor, going from left to right, and then the e to the negative x as the second factor. All right. Now, so if this question were asking about increase or decrease, then this is the function we would have to set equal to 0 and figure out where it's positive or negative and so forth, right? But that's not what we're doing. We're doing concavity, so we have to go to the second derivative. And again, we need to do our product rule. The derivative of the first now is negative 1 times the second, and then plus the first, the 1 minus x, times the derivative of the second, which again is e to the negative x times another negative 1. All right. So let's carefully handle these negative signs. Now, again, notice you have a e to the negative x in common, because no matter how many times you differentiate the e, it never goes away. So I have e to the negative x, and then in parentheses, I have this negative 1, and then I have plus, then I have 1 minus x, but then that's also multiplied by a negative 1, so right there. And then when we simplify this, let's see what we get in parentheses. So we have e to the negative x, and then in parentheses, we have a negative 1. Distribute that negative 1, so we have another negative 1, and then we have a plus x. So this is our second derivative. And again, I'll put the polynomial in front. I have x minus 2, right? Negative 1 minus 1, and then times e to the negative x. All right? So the idea is we have to figure out where the second derivative is positive, where the second derivative is negative. So first, let's find the zeros, because again, I want to use the number line, because the number line, we can get our answer in a very efficient way. We can solve both inequalities essentially by doing one process, right? So first question, where is our second derivative equal to 0, right? Well, it's already factored for us, so that should be helpful. So we have this equal to 0. So there are two factors here. So either the x minus 2 must be 0, or the e to the negative x must be 0. But going back to properties of exponential functions, basic exponential functions, they never touch the x-axis, right? The x-axis happens to be a horizontal asymptote. So this equation has no solution. If you tried to take the ln of both sides, you would end up with this. You'd end up taking the natural log of 0, which again is undefined. So no solution, right? So no solution there. So then the only value of x that works is x equals 2. Right? So there's only one value of x at which the second derivative is equal to 0. I don't know if there's actually a sign change there. I have to see if it goes from plus to minus or minus to plus. And that's where we can use our number line, right? So our number line, again, is drawn to reflect the domain, which goes from negative infinity to positive infinity. But now I just have one value of x. I really just have two intervals to check, right? So again, we can use test points. So if I use, let's say at x equals, I'm going to pick 0. Remember, our second derivative is, in fact, it's right here. So if I plug, here's my second derivative. If I plug 0 in, do I get something positive or negative? Well, I'll have 0 minus 2 and then times e to the 0, right? Well, this is a negative number, so I get something negative. So what that means is, in this interval, my second derivative is negative, right? Again, let me label this number line so we are clear that we're now talking about the second derivative of our original function, and that second derivative is negative between negative infinity and positive 2. What about between 2 and positive infinity? Well, pick any number that's greater than 2. Let's say we pick x equals 3, then f double prime of 3, that's equal to, so it's 3 minus 2 times e to the negative 3 power. This factor is positive, the e is positive, so the product is positive. So our second derivative actually changes sign. So I can now say that my original function is concave down on the interval negative infinity to 2, and then concave up on the interval 2 to positive infinity. Therefore, at x equals 2, my original function has an inflection point. So that's my summary. Let's write it down, right? So remember, here's our function now, just as a reminder. So this is the function whose property we're about to describe. We just happen to use the second derivative to understand what that property is like for this function. So for this function, f of x is concave down on the interval negative infinity to 2, right? And concave upward, so concave up on the interval 2 to positive infinity, right? And then we can say at this point, so at x equals 2, f of x has an inflection point. So at x equals 2, again, this function has an inflection point. Right? So there we've used our second derivative to determine the intervals of concavity and determine where the function has an inflection point. Right? So yet another important property that can be analyzed using the derivative. Right? Hope you found that interesting, and I'll see you in the next video.